to it. I can use those trig substitutions I got from pre-calculus. Same thing with tangent and secant. There's one for cotangent, cosecant, sine, cosine. That's substituting with pre-calculus. And sine squared plus cosine squared equal 1 really is the Pythagorean theorem on the unit circle. The hypotenuse. So x squared plus y squared equals 1. That's what we're saying. Oh, today we're going to look at a little bit more trig substitution where you're not even going to think, trig, where'd that come from? At least in the ones we did yesterday, you saw sine, you saw tangent, you secant, cosine, you saw it. You knew it was trig. Here. First of all, know those integrals, trig integrals, that we have. Okay. If I have an integral of this form, it's going to be pretty difficult to integrate. Pretty difficult than if I had this with an x out front. Because this is going to be a constant minus x. So if I was going to say, hey, let's let u be this, I see I'm going to have to bring down the 2x and x dx, and oh, there's x dx, but I don't see no x dx here. What do I do? That's going to be kind of hard to do. And then there's second. These are trig substitutions that are effective because of these identities over here. Because of these identities and the Pythagorean theorem, these are true right here. You don't necessarily need to know they're true right here. Because of these. Okay, you don't have to know. Because of these, I can say this. Because of this. So notice the expression there. We just said that's going to be difficult to integrate without an x out. So if I have something like this, the square root of two things being squared, I can do a trig substitution. Most people go, how do you know it's trig substitution? Well, it's going to be Pythagorean theorem oriented. That's why. And because of those ideas. Okay, we don't have time to prove them. But when you see the square root of two things being squared, I would think trig substitution. Okay? And if you've got these in your notes, this becomes a sine, this becomes a tangent, this becomes a secant. Gives me something to work with. Is that cool? We've also got these for inverse. These are the ones people really hate. Because you never think of inverse. But we're going to do one. Maybe two. So in your yellow sheet, you want to get, if you see square root of two things being squared in this way, be careful because this is variable minus constant, this is constant minus variable, and then this is constant plus variable. So this could have been written the other way. This, of course, is the same as square root of x squared plus x squared. So I don't need that new version, but that's two different versions. Okay, so I need those, and they become that. So in your yellow sheet, we're putting our formulas on a yellow sheet so I can
give you one.
You gave him one?
No, I don't give you one.
Oh. Well, I got more too. You don't have to write down this whole thing. And this is on Canvas too, so you can go back and look at it. You really just need this part right here. You really just need that. And I would.
35.
Yeah, be careful. These are on Canvas. These are the inverse ones. So inverse, I've got, oh, this is occurring in the denominator, something, two things being squared. In the denominator.
So we don't need to copy that one.
So these three and these three.
We don't need to.
Well, if you don't. You don't have to know everything about everything to make a 5 on the.
Ah, I know that.
So you know these?
Mm-hmm.
Wow. Those are the ones people usually say, you know, I'm gonna study 3-4 hours on just these and I'll still not get
I'm
it.
trying to find it.
So it's not worth my time. Sometimes playing with these, they kind of sink in after. These, it's like, but I'm gonna present them to you. And they are Pythagorean theorem based because you got two things being squared. And so let's see what we can do. Again, if you see trig functions in there, you can kind of play around with those and see if your trig identities work. If you don't see trig functions, when can you bring in trig? Well, if you got two things being squared, especially under a radical. Because that's Pythagorean theorem, right? Two things being squared, take the square root. Less obvious is this if it's in the denominator. Who's ready for some fun? Okay.
Wait 1 second. Yes.
And again, it's on campus, so if you go back to lesson 6A, you'll see these are our notes. And so I guess we went through 1 and 2, so here's 3. Actually, yeah, we just need to practice this stuff. So here's question. Let's make that one. Even though you got it. Okay.
The table
You
here.
know what I see?
The table here.
I see the square root of two things being squared.
Yeah. Yeah.
And I know that the square root of two things being squared, that this,
You have a pencil.
because I just scrolled past it,
Pencil. Pencil. Yeah.
a squared, constant, some constant being squared minus variable being squared. I could just call that a sine theta. Alright, so, hey, maybe I can use that. So here's what I'm gonna do. I'm gonna let x this is gonna look weird, but this is the first time we've seen it. And then I'm gonna get, well, derivative of x, bring the 3 out. What's the derivative of sine? Cosine. Theta. Oh, theta. Our variable here is theta, not u, not x, not t. You can make it something else. Okay, so now I'm gonna go back over here. And the reason I did this off to the side is because I saw the square root of two things being squared. 3 squared is 9, and of course, x squared is x squared. Okay. So in the top here, look what I get before I put it back here. Using this substitution, I said x is 3 sine theta, right? And that gives me this, just the top part. Because it's the top part I'm kind of focused on right now, because it looks weird. That bottom doubles. 9 minus 9 sine. And that'll give me, let's see, both things have a 9. That'll give me 1 minus sine squared. And that radical. And it's that radical that was the troublemaker here. Oh, look at this. Then I got 9. 1 minus sine squared is cosine squared. So the square root of 9 cosine squared is just 3 cosine. New variable. That's that troublemaker in the top. I changed it to a trig function. Why would you change it to a trig function? Well, if we tried to use substitution here, it wasn't going to work for me. Trust me on that, it wouldn't work for you. And then I see that square root of 2 things being squared. Okay, so I try that. Maybe I try it in different ways, but hey, I see that, would definitely be that. What's A? What's, right? A sine. Okay, so this gives me now, so the integral of that will equal that square root up in the top really is just this, 3 cosine theta. Just gives me that in the top. In the bottom, I got x squared, but remember, we're changing x. X squared is really gonna be 9 sine squared, because I'm squaring it. I'm gonna plug it in right there and then square it. Should I do this first so you see it in your notes? We still got dx, we haven't done anything. Dx is this, right? So I can go ahead and change this dx. 3 cosine theta d theta. And then we'll clear this. Look at that, I got 9 cosine squared in the top. In the bottom, if I square that, I got 9 sine squared in the bottom. And I got this d theta. So now I can take the integral in terms of the theta. The 9s will just cancel, right? I mean, I can pull them out front, but you got 9 over 9, so that's more. So you really just have that. What would you want to do here?
You see that it's tangent square, maybe, the inside.
Did you say cotangent square? Is that what you said?
I said tangent, no, yeah.
Because it's cosine
Yeah.
over. Yeah. Okay, we'll try that. Do I have the integral of a cotangent square? Is that on my yellow sheet? Or a derivative that got me cotangent square? You may say that's not gonna work. I don't give up yet. Cotangent squared, if I use one of my pre-calculus identities, I think that's cosecant squared minus 1. And I bet there is a formula that gives me cosecant squared. Because I can do this. What do you think? Hey, this is just gonna be the variable, right? And then plus c because it's indefinite. So that's just gonna be the variable plus c. What is this one? What's the integral of cosecant squared? Yellow sheet. You either have a derivative saying if you take the derivative of this, you got cosecant squared, or you got an integral of cosecant squared telling you the antiderivative is something. Should be on there twice. It's probably on there as the integral of cotangent, or I'm sorry, the derivative of cotangent is negative cosecant squared. You think that was the fun part? We gotta put it back in terms of x. How are we gonna do that? I mean, this is our substitution over here. I don't know how we're gonna substitute. Oh, I think I do know how we're gonna substitute.
You theta by 7.
That's my go-to triangle for pre-calculus or trig specific. Hey, this was my let x be this, so sine of theta must equal x over 3. Sine of this must equal x over 3. Because it's opposite over hypotenuse. Therefore, if I do the Pythagorean theorem, I get this. This squared minus that squared, take the square root. Guess what that is? This squared minus that squared, take the square root.
X squared.
Yeah, I got all three sides. So I would say this part right, well, we got the C plus C. This, the angle, sine of theta equals x. I would say minus inverse sine of x over 3. Oh, that brings the x in. Gets rid of my theta. So theta would be inverse sine of that. Okay, that's theta. What about cotangent? Well, specifically, it's negative cotangent. Isn't cotangent adjacent over opposite with a negative sign in front of it? There it is in terms of x. Hey, it's trig function, so if I'm trying to get back to x, right triangle. Especially since I let x equal this, it'd be real easy. Well, there's two sides of my right triangle right there. Yes, it looks bizarre. This is why people don't like it. But this is also the first time we've done it. You could probably at least take an effort or take some steps towards this answer. And if it was a free response, get some points. Where's your questions? This whole thing started because of this thing right there. Causing a problem. So I went to my yellow sheet. I said, what can I really call this thing? Oh. There we go. That's the thing that unlocks. That unlocks everything, and this unlocks everything, putting it back in terms of x. But of course, we had to put it back in terms of x because it was an indefinite integral. If it was a definite integral, guess what we could have done? We could have changed my intervals of integration and not have to put it back in terms of x. Yeah, we could have just used this. I'm telling you, that's an easy. That's a time saver if you got to plug in numerical values, get a definite answer. Can I erase this and at least get the next one set up? Everybody got this? Just know, you don't have to know everything about everything to get a 5 on the AP. And if you were in a calculus class in which you were playing with these for weeks, it would sink in, okay? Here I'm presenting it to you in a few days, and then we're moving on to something else, okay? We just don't have the latitude to sit here and say, hey, let's spend the next 3 weeks on trig integrals. And in college, you probably will be able to do that. Okay, so number 4. You're gonna love number 4. Because you're not gonna see this coming. But I've told you something about if you have a common denominator, right? Break it up. Bummer. I don't have one term. I mean, I do have a common denominator, but it's gonna be x cubed over this 2 terms, 3x squared over those 2 terms, minus 1 over those 2 terms. Man, it was great if it was over 1 term, because I could just use that to cancel the top, right? Or bring it upstairs and call it negative x. This is a good one, because what do you do if you have more than 1 term in the bottom? it's not so easy to break up. I mean, you could break it up, but I don't know what that's gonna get you. We're gonna use our old friend way back in the day. I look and see what this is telling me to do. It's taking this over that, which means this divided by that.
So this times that.
No, take this numerator. We're gonna use long division.
78 days of school on school.
And we're gonna divide by
That would be
this.
cool. Spring break.
Take that and divide by that.
How?
Let's see.
That was you could do this to me.
Let's do what it says. I mean, I could put it every term up here over those two terms, but I think you would do that and you would go, now what do I do? And so I'm gonna say, let's do what it says. Maybe that'll help me. Maybe it won't. But maybe it'll help me if I do what it says. Okay, like any long division. This is like a 2-digit number out here, but I got 2 terms out here. Think of something I can multiply this by to get this first term right here, which is x cubed. X. I'm gonna put 0x there as a placeholder. So I got the third power, second power, first power. Okay, you just said multiply by x.
Yes.
So x times x squared is x cubed. But then there's a second thing. X times 1 is x. So I line up the like terms, because you know what I'm gonna do. I'm gonna subtract, remember 3rd grade? Subtract this row from that row. The whole point is you're trying to get rid of that, which you did. This minus nothing is 3x squared. And this minus that is minus x. That'll bring down this.
You just
Do it again.
multiply by 1.
How can I make x squared look like 3x squared? What can I multiply by?
3.
3, that will go in the constant column, positive 3, right? So that gives me 3x squared, and 3 times 1 is 4. I'm now gonna subtract this row from the row above. Get rid of that, minus nothing, minus 5. Hey, that's as far as I can go. But you know what it gave me? This equals the integral of this answer. Oh, there's a remainder. Right, there's a remainder.
Don't you divide it by the,
Yep.
then we divide
But
by.
I did get, that's the integral of x plus 3, and there is a remainder.
You just
I'll
add
just
it.
pull out the minus. And so if I pull out the minus sign, that's x plus 5. Over whatever I was dividing
How did you get? Okay, no.
Be great if it came out even and no remainder, because look what I got here. I got 2 easy terms to take the integral. And 1 maybe not so. So this part will be pretty easy.
Yes.
I mean, that is what we had up there, but maybe it's a little simpler than we had. But let's go ahead and do this. It's gonna be pretty easy. Yeah.
Why is there a 4 in the division?
Oh, Yeah, guys, that's a good question. Because 3 times 1 is 4.
Yeah.
Sorry.
Yo sabía.
4.
No, it wasn't your question.
Yeah.
Then you said that you.
Yeah.
Yeah.
I was.
Good question. And then I just. Hey, this is pretty easy right here. This is just x squared over 2, right?
Yes.
And that's 3x to the 1 over 1, 3x. Oh, then I got that. And then I'm gonna have this.
X squared plus 1. That looks like a trig identity.
Yeah, do you like trig identity? Okay.
You can separate.
How are you with a u substitution?
You can separate the fractions. And
U sub's cool.
You could.
like the first one is x divided by x squared plus 1. And I think you need to divide again. No, I remember what it is. And the second one is 4 divided by x squared plus 1. Before you take it out, and it's going to be
Minus both, right? Minus both.
and the last one before you take it out, and there's a formula for that one. It's like tangent negative 1. I think it was.
Well, what do we wanna do here? Do you wanna use the trig substitution?
Yes.
Do you?
No.
No.
You know why? I don't want to.
Because it stinks.
Because if I let u be something, the more complicated part, and I take the derivative of that, I'm gonna get 2x dx. X dx. U equal x squared plus 1. Du equal 2x dx. Oh my god, I see that x dx up here. So 1/2 du equal x dx. Oh my god, that's a simple substitution. So now I'm gonna get, hey, we'll worry about this one tomorrow. Minus the integral of 1 over u du. 1/2 du, sorry. X dx is 1/2 du. Minus this one coming up. Nope. Yeah, we might have to because the derivative of this has an x in it, I don't see an x in here. So we might have to revert to a trig substitution. But at least it's a pretty basic one. So that's pretty easy, right? X squared over 2 plus 3x minus, bring the 1/2 out. What's the integral of 1 over u? You know that one.
1 over u.
Yes.
Negative log.
Yes, because I natural log of u. Or we can go ahead and plug that in because u is x squared plus 1. Okay, we got that one, we got that one, we got that one, we got the plus c at the end. The only thing we don't have is this one.
You just take the 4 out, and by the rules, use tangent negative 1.
Oh. What if I do that? Does that help me locate an integral? 1 over the square root of something squared plus something squared.
Tangent.
Integral of 1 over something squared plus something squared. Inverse tangent. We finished it, guys. Almost. Wait, inverse tangent of what?
No.
U over
X.
Which is U and which is A?
It's X, right?
Oh, U is X. A is,
Over 1?
A is there.
Let's back up, we already finished this one. I got one more thing to say here. There it is. This is the thing that just takes practice upon practice upon practice, which is why I'm saying,
Ah, with the same thing as X. Yeah.
if you had weeks to do
It's the
this,
same thing as X.
in the practice,
Why would you write X over 1 instead of X?
you can just do it. Just to show you that you had U over A.
I'm pretty sure that the one that you do this substitution, there's a rule that you don't need to think about it, you just apply it and you don't need to do substitution. Like you just know.
If you know that, yeah, bring it up.
Like I know, but
Can you show